Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to discuss about autocorrelation. Basically, it occurs in a time series framework. When data are ordered in a chronological order, it may be possible that error in one period may affect the error in the next period. It is very likely that there is a intercorrelation among the successive observations. For example, today's temperature is dependent on yesterday's temperature. Today's stock prices are dependent on yesterday's stock prices, and therefore there is a correlation among these observations. Now, because of this, we are getting a special type of error which is known as autocorrelation. Now, if I talk about this multiple regression analysis, in this, independent variables are influencing the dependent variable, and then there is one error component E, epsilon. Now, in case of autocorrelation, these two errors may be the error of today and the previous error, that is epsilon t and epsilon t minus 1. They are not free of each other, they are influencing one another. The most common patterns which can be captured with the help of regression are linear additive trend, exponential multiplicative trend, quadratic trend, additive seasonality, and multiplicative seasonality. But wait, there is one more pattern which can be captured, and that is a pattern which is autocorrelation. Basically, it is a correlation between the series and the past values. So if we consider lag 1, it's an autocorrelation between yt and yt minus 1. That is a present observation and the previous observation. If we talk about correlation between pair of values at certain lags, so the autocorrelation between yt and yt minus 2. So if I say that there is a correlation between today's observation and yesterday's observation, how to detect it? It is detected with the help of autocorrelation function. Here, whenever these spikes go out of this dotted line, it means that there is a significant correlation existing among these legs. Now, the basic question is autocorrelation good or bad? So, it's good as the series having more information which we can still capture, which is not possible in the traditional model, but with the help of this, we can capture it. Now, common autocorrelation which can exist is it may be possible that your values may be high values followed by high values, low values followed by low values. Just like a poem, Twinkle, Twinkle, Little Star, How I Wonder What You Are. You can see here. It may be also possible that there is a negative lag. High values followed by low values followed by high values. Low, high, low, high. So that is negative lag, and this is swings. The positive lags are known as stickiness. It may be possible that the positive lags may be existing at some particular interval, that is m, 2m, 3m, and that is a seasonality in the data. You can see the swings are, the pattern is getting repeated. The nature of autocorrelation, the randomness of the sample implies that the error terms for the different observations will be correlated. But this does not happen in the time series data because the successive errors will be correlated with each other. It is also possible that the current error term contains not only the effect of current shocks but also the carryover from the previous shocks. They are correlated, and because of this, the autocorrelation exists. The possibility of autocorrelation should always be entertained when we are dealing with the time series data. For the better model, always include this thing in the model. For efficiency, all systematic information needs to be incorporated into the regression model. So autocorrelation is a very systematic pattern in the errors that can be either attracting, that is positive, or repelling, which can be included in your model. There are some instances which show what is a positive autocorrelation. We have already explained this. High followed by high, low followed by low. This is the case of no autocorrelation. Negative autocorrelation, positive followed by negative, negative followed by positive. Now, there are some assumptions of classical linear regression model that the covariance between the two successive errors, that is, the two disturbances, should be equal to 0. But in case of autocorrelation, in case of time series, this thing is violated. Now, as this is violated, what will happen is if I consider the error at t, And if I consider the error at t minus 1, and if I run the regression, so I'll get some value of rho. This is known as a first order auto-regressive scheme. If you are considering more than 2 time periods, it can be said a dynamic model. Now, depending upon the value of rho, what are its implications? If rho is equal to 0, then we have no serial correlation, but obvious. See, if rho is 0, naturally there is no autocorrelation. Now, the rho can be 1 or rho can be minus 1. Now, if rho is equal to 1, so if rho approaches the unity, the value of the previous observation of the error, mu2 minus 1, becomes more important in determining the value of existing current error term. If rho approaches negative, obviously the strength of serial correlation will be very high. This time we are having a negative serial correlation. It is just like a sawtooth, positive, negative, positive, negative. What can be the consequences of autocorrelation? So in the presence of autocorrelation, the OLS estimators remain unbiased, consistent, and asymptotically normally distributed. They are no longer efficient. As a consequence, the usual T, F, and chi-square cannot be applied. The usual T and F tests are not valid and will tend to be higher, indicating higher significance of our estimates than the corrected one. The OLS estimators will be inefficient and therefore no longer blue. Blue means based, linear, unbiased estimator. Third, the estimated variances of the regression coefficients will be biased and inconsistent, and therefore the hypothesis is no longer valid. Fourth, under estimates, the variances of the error term is likely to overestimate the true variance. In most of the cases, R square will be inflated, or it is also known as overestimated, indicating a better fit than what is existing truly. In the presence of error, in the presence of autocorrelation leads to unexplained variances. Unexplained variances lead to underestimate, and the statistical predictions become inaccurate. What are the effects of autocorrelation? The effects of autocorrelation are: the positive autocorrelation will create a downward bias on variation, which will lead to high t values, which will lead to high probability of type 1 error, and which will lead to probability of rejecting the true null hypothesis. For detecting the autocorrelation, we are having the Durbin-Watson test. The Durbin-Watson test can be only carried out under the following assumption. The first assumption is the regression model should include a constant. The second thing is it should be a first order autoregressive scheme, that is sigma t minus 1. If we are having AR2 or more than if we are having more than AR1 process, Durbin-Watson test will not run. Third, the equation does not include the lag dependent variable. Say for example, if you have included the yt minus 1 in the model, then the Durbin-Watson statistics will not work. The fourth is there should not be a missing observation in the data. Fifth is explanatory variables are non-stochastic or fixed in repeated sampling. Sixth is error terms should follow the normal distribution. What is the hypothesis? Hypothesis is rho is 0, no autocorrelation. I am talking about which row? This one. This row should be 0. If rho is greater than 1, then there is a positive autocorrelation. If rho is less than 0, then there is a negative autocorrelation. Now let's try to understand the concept of the Durbin-Watson statistics. The D is calculated, that is a summation of the errors are taken, that is a present error minus previous error, square of it, and the summation of the present error. If I expand this, A minus B square, so A square plus B square minus 2AB. Now in the long run, this two will be same. So if I say that mu t square is equal to mu t square, this will become 2 mu t square. Now when I'll divide with this, I'll get 2 minus 2 So the equation is D is equal to 2 into 1 minus mu t minus 1 mu t square. So now rho estimate is this value. My Durbin-Watson is equal to 2 into 1 minus rho estimates, rho hat. Now, how to conclude it? If rho is equal to 0, D is equal to 2, therefore the value of D near to 2 indicates, it means that if this is 0, means that we don't have any autocorrelation. So the value of 2 indicates that there is no evidence of serial correlation. And therefore, the Durbin-Watson statistics ideal value is 2. Rho is equal to 1, then we get D is equal to 0, which indicates a strong positive autocorrelation, means that rho will be close to plus 1 and thus D will get very low values for positive correlation. If rho is minus 1, D is 4. Similarly, when rho is close to minus 1, then D will be close to 4, indicating a strong negative serial correlation. What are the limitations of this test? This test can only handle AR1 schemes and it is not a powerful test. We can also detect autocorrelation with the help of graphs. For this, I'll be using the data set of Damodar Gujarati from the book Damodar Gujarati. That is a basic econometrics. You can very easily download the data set from here. All the data sets are available. I'll be working on chick data set. So I'll click on it, open. So I'll get the value PB, PC, Y and YD. I want to make Y as a dependent and that, so I want to run the equation quick estimate equation Y dependent variable C, PB, PC and PD. Sorry, YD. Click OK. I have got the estimates. Basically, I want to detect is there a presence of autocorrelation or not. So here the residuals are there. So these are the present residuals. Now I want to get the residuals of the previous. So how can I get it? First of all, I'll have to store this residual at some place. The command for storing any the command for generating any new variable is generate resi 01 is equal to reset. It will simply store this residual at some location. Now, why this thing is necessary? Let's try to understand. If I run this equation again, this is the system variable. And therefore, this value will change. To freeze this value, we are creating a new variable that is resi01. Now, I want to see that is there any relationship between the present residual and the previous residual. For that, I'll generate the scatter plot. Command line is scat resi 01, that is minus 1, the previous error with the present error, resi 01. Run and you will get the graph. Considering the graph, I feel that there is some strong correlation which is existing between these two residuals, and therefore it indicates that there is a possibility of autocorrelation. The same thing I can also plot it using the command plot resi01 minus 1 resi01, and I'll get this type of graph. It clearly indicates that there is some correlation which is existing between these two residuals. Now, all those who are not able to see the command, I have written it in the Word file. You can see here now. Generate resi01 is equal to reset scat resi01 minus 1, that is the previous error with the present error, resi01. Plot resi01 minus 1 resi01. Now you again go in the equation and see the value of Durbin-Watson. How can I get the values? Here it is. You can see the value is 0.89776, which is a very strong indication of autocorrelation. We already know that the Durbin-Watson test can only be used when we are having a first-order autoregressive scheme. Now here, we cannot use Durbin-Watson statistics because we are having the lag of the dependent variable, and therefore Durbin-Watson statistics cannot be. So if you want to check serial correlation, now we can use Q statistics or LM test. So how we can do this? There are two methods. One, the graphical representation, and another is a test. For this, I'll again go back here, view, residual diagnostics, serial correlation, or rather correlogram Q statistics. Likes to include 20, click OK. And you will find that the p-value of all this is less than 0.05, which is not desirable. It means that there is a presence of autocorrelation. Now, when we are having more than first order autoregressive scheme, that is rho t is equal to rho t minus 1, then in such scenario, we are using breuschgodfrey LM test. So my present error is dependent on many past errors. The null is rho is equal to rho 1 is equal to rho 2 is equal to all of them are 0, or in other words, no autocorrelation. The alternative is at least one of the row is not 0. How to carry out this test? In EViews, for this, I'll have to go here, view, residual diagnostics, serial correlation, LM test. Click OK. And I got the result. This thing we can copy very easily. Right click it, copy, and take it to the Word file. The same result. What's a null hypothesis? There is no presence of serial correlation. Alternative is there is a presence of serial correlation. The interpretation will come from this value. As the p-value is less than 0.0029, that is, as the p-value is 0.0029, which is less than 5% level of significance, we reject null hypothesis, which means that residuals are serially correlated. Next thing which we have to see is the individual p-value of the residuals. So you can see here that the p-value of the resid 1 minus 1 is less than 0.05. Therefore, it clearly indicates that it is an AR1 process because the p-value is less than 0.05 and therefore resid minus 1 is significant. Now, what are the remedial measures for us to handle this autocorrelation? The first remedy is to include the one lag of the dependent variable into the independent variable to capture any additional information. So how we can do this? Directly go here in estimate, and now I'll include y minus 1 and I'll try to monitor what is happening. Let us see the Durbin-Watson statistics. Reasonably, it is now near to 2. The second remedy is to include the autoregressive term directly into the model. How we can do this? Let's go into the EViews. This time, again go in estimate, remove y minus 1, and instead of this, write down AR1 process. Click OK. And you can see again the Durbin-Watson is now near to 2. Now, third remedy is, depending upon the value of Durbin-Watson, that we are having two remedies, third and fourth. So if the Durbin-Watson is less than R square, then your first order differencing may resolve the problem. We know that the maximum value R can take is 1, which means that D is less than 1, so it is a case of the positive autocorrelation. The Durbin-Watson is greater than R square. Here, D is more than 1, so it is a case of negative autocorrelation, and this can be resolved with the help of Cochran's orcutt method. Let us try to resolve the first scenario, that is when Durbin-Watson is less than R square. But before we carry out this analysis, let us try to do the residual diagnostics of the previous one also. So, say for example, the first remedy which was there is y minus 1. Click OK. We'll go in view, residual diagnostics, and we'll try to see the parallelogram Q statistics. And you can see the p-value of all of them is now more than 0.05, which is much more desirable. Let us try to check this, the same thing with the help of serial correlation LM test, click OK, and we have got the p-value which is more than 0.05, which is quite desirable, which means that there is no serial correlation. The first remedy. Second remedy, instead of y minus 1, now I will use AR1. Let us try to see now the residual diagnostics of this also. View residual diagnostics, again go in Q statistics, click OK. Again you see the p-value more than 0.05, quite desirable. View residual diagnostics serial or correlation LM test. So it's not performing. Okay, fine. So as we have included AR1 process here, this test is not working. Fine. Let us go back, estimate. This time we want to take the difference of all these variables. The third remedy. So we have taken the first difference of dy, dpb, dpc, dyd. Just click OK. And you can see I again got a Durbin-Watson nearer to 2, which is the ideal value. I'll again check the correlogram Q statistics. Click OK. And you can see the p-value with all of them are more than 0.05, which is quite desirable. Again, go in View, Residual Diagnostics, Serial Correlation LM Test, click OK. This value is more than 0.05, which is also quite desirable. Now, the commands which I have used are ls, yc, pb, pc, the basic first regression. This is a remedial measure in which I have considered the dependent lag of dependent variable. In this, I have considered the AR1 process. Here, I have considered the first difference of all the variables. Make sure that when you take the first difference series, you don't take the difference of constant, because the first difference of constant is 0, and therefore we are not including constant in the differentiated model. Now comes the fourth remedy. What to do if my Durbin-Watson is greater than r squared? So in such scenario, what we do, we take the difference with the intercept rho, whatever our Durbin-Watson is. So yt minus rho, yt minus 1, b0, 1 minus rho. Similarly, all the series are taken, that is, a difference is taken, yt minus rho, yt minus 1, pct minus rho, pct minus 1. So the series is generated on this basis, and then we will run the regression. So what is the value of the rho which we will consider? We will consider the first value, a basic regression equation, y, c, pb, pc, yd. So I'll consider this value of rho. And therefore, all the series will be generated on the basis of this. Generate PB1, which is equal to PB minus 0.8977. Directly, we have taken the value of Durbin-Watson, PB minus 1. Similarly, PC1, YD1, Y1. Let's try to generate this series in EViews. So, PB1, again, I'll go back here and I'll copy this command directly from here. Copy. I'll get PC1. Similarly, I'll take the value of YD1, copy, YD1, and now the dependent way, copy. Enter. Let us try to check. Is the series generated? Yes. YD1, PC1, PB1, and YD1 is also, Y1 is also generated. Now I will run the series on this new variables. So ls is equal to y1 constant, pb1, pc1, yd1. Enter. Ls is not defined. Okay, I have to not use ls in this window. I'll say okay. Yes. You can see the value of Durbin-Watson statistics again. It's near to 2.15. Quite reasonable. View, residual diagnostics, parallelogram Q statistics. All values are more than 0.05, so the serial correlation has been removed. View. So these are 4 remedial measures by which you can handle serial correlation. Now we will conduct a test, serial correlation LM test. Click OK. You can see here the value again is more than 0.05, quite desirable. Again, we'll come on the estimates. Quick estimate equation ls y1 c pb1 pc1 yd1. Click OK. ls is I have got the estimates. Now you can use these estimates directly, but in the case of constant, you will have to change it. The change is shown in my slide. You can just see this. So here, Durbin-Watson is 2.158. So the coefficients are corrected, but the coefficient of constant is not corrected. So the intercept has to be corrected using the formula alpha original divided by 1 minus rho. So 2.594 upon 1 minus 2.158. So I get 3.495. So this was all about autocorrelation, how to detect it graphical in 2 methods. One is using graphical representation, another is a test, and there are the remedial measures which we have talked about. So thank you. For more videos on econometrics, you can subscribe to my channel. You can follow me on LinkedIn and Twitter.